Hello and welcome everyone, and thank you, Richard, for reaching out and inviting me to give this talk. I feel very delighted. So my name is Emanuel Larsson, and I am, let's say, working for Lund University, and also under Lund University there is a Synchrotron called Max 4, and I'm also connected to a lot of other, let's say, platforms and let's say institute and affiliations at Lund University. The outline of this talk. Let's see, a little bit slow here, is that first we will take a look at the technical evolution of X-ray and neutron tomography, followed by how does tomography actually work, and then an overview of some selected synchrotron light sources all around the world, followed by educational activities related to the so-called KBLT scanner, which stands for kitchen-based light tomography. And then I will say a few words about developing user-friendly reconstruction, let's say software or workflow. And then we will take a look at some further KBLT scanners because this project has spread around the world. And then we'll finalize with some links to further info about the project. So yes, to put everything in context, I'm sure that all of you have heard about a so-called CAT scan or a CT scan, which you commonly do in the hospital. And let's say X-rays were detected already in 1896 by Carl Wilhelm Röntgen. And then it took, let's say, till the 70s before the world saw its first CT scanner. And then, let's say in the 1980s, this is a so-called popular science summary, let's say, of the field. So everything might not be exactly accurate on the year, but it gives an overview of the happening, let's say, during this decade. But then in the 1980s, also there was an interest to, let's say, re-engineer the CT scanner and make it more suitable for high resolution imaging, especially in rodents. So this you can call a preclinical X-ray CT scanner or other sciences started getting interested in tomography. So they also then invented another version of, let's say, microtomography, where instead of having the sample laying still and having a detector around and X-ray sources circulating, instead one has the X-ray source fixed, the camera fixed, and instead one rotates the sample. And then with the time, let's say, and let's say, the invention of so-called synchrotron, synchrotrons and synchron radiation, this technique, microtomography, could move into the synchrotron. And so today we have so-called synchrotron X-ray microtomography, and with time and with adding some X-ray optics, one could also push the resolution and we could go down to so-called the nanoscale. So we would have nanotomography. And you can see that for these techniques, we have a really, let's say, narrow field of view. For microtomography, we can say that we have a field of view in somewhere in the regime centimeter to millimeter. And while as for nanotomography, we're speaking about having a field of view of micrometers, let's say, but you get the resolution of in nanometers. But in parallel to this, there were also other initiatives where instead one wanted to have a broader field of views, but at lower resolution, as in this example from Fraunhofer or Audi in Germany, where they can do a CT scan of an entire car. And if you take a look at the evolution of neutron tomography, you can see that also this discovery of the neutrons also was awarded with a Nobel Prize, just as Carl Wilhelm Röntgen. And one of the first nuclear reactors was actually in Detroit, and it was used for inspecting, let's say, car parts. And then with time, there were also more reactors built. And already in the 1964, one had the first neutron radiograph, which means in 2D. So tomography is in 3D, radiography is in 2D, here of a human chest. And then in 1968, there was the first drawing of what neutron tomography could look like, but one had to wait another, let's say, 12 years before one could actually test out neutron tomography to image samples. And here you can see that they had 200 projection images with a spatial resolution of around 1.3 millimeters. And then as let's say the evolution continued, one would also have neutron tomography, meaning then 3D at these neutron facilities. And today they even combine them with X-ray. So you can have neutron tomography, neutrons in one direction, and 90 degrees toward the neutron beam, you can have a small X-ray source. So you can do sequential or combined X-ray neutron tomography to take advantage of both contrast modes. There are also companies producing smaller, let's say, sources of both X-rays and neutrons. And also in Uppsala, which is in Sweden, Uppsala University, they have also constructed, which is a PhD thesis, they have also constructed a more lab-based version of neutron tomography. But in general, neutrons are much slower than X-rays, that we can say. But quite interestingly is also that in Australia, they actually, SCyro, actually have an air cargo scanner that can scan smaller cars or even containers containing various features. So I think this is a nice feature to have, let's say, in customs control. So with that, we move on and we take a look at how tomography actually works. So here I will present the first version of my scanner that I constructed in 2018. So to do tomography, you need, let's say 4 to 5 different things. You need a light source, you need a rotation stage, a sample, a detector screen, and a camera. And this experiment I did on a, let's say, early Friday night, late Friday night, early Saturday morning. And I managed actually to scan this sample, and I rotated it by hand, and I had a ruler to measure how many degrees I was rotating. And by the time, let's say we reached 2:10, my wife came out into the kitchen living room and said, "What are you doing? Go to bed." And then I said, I actually just scanned and reconstructed your shampoo bottle. And then she said, "Cool," sat down and said, "Now show me something else." And then I scanned this plastic screw. And then I scanned a few more samples. But then give it, let's say, another 3 to 6 months. And then I had optimized things. So then I had this version of the so-called KBLT scanner, kitchen-based light tomography. So this one actually runs on Raspberry Pi, which is behind this touchscreen. I have the same light source. I now have a more optimized, let's say, detector, a USB camera connected to the Raspberry Pi. And I have a rotation stage, as we call it in tomography. You can also call it a stepper motor. And this stepper motor I use to rotate the sample. I also added some more features. For example, a stepper motor here for translating the sample outside the field of view, because we want to do something called the flat field, so that we can normalize the images before we reconstruct. And I also added relay modules so that I can control these translation motors, because I have 4 of them. I have one below the source, one below the sample, one below the detector screen, and one below the camera. So I can move them to get different field of use or more or less intensity from the light source. And I also added speakers, and I have, if I'm not mistaken, somewhere between 12 to 15 warning messages recorded in various languages, saying, for example, "Attention, lights will be switched on." Of course, we're not dealing with X-rays or neutrons, so the light is not dangerous, but it's a way to, let's say, make the user familiar with the fact that you might hear warning messages when you are at a synchrotron or neutron facility, and you should not be scared, but pay attention, let's say. And to operate the scanner, I also program a graphical user interface, so a GUI, where I can turn the camera on and off. I can start the light switch, and that was actually very easy. I just hacked the on-off button with 2 cables, actually. And then, let's say, we can translate all these features, the source, the detector screen, the camera. And and here to make an overview of the results, let's say, you can see that I scanned this so-called Lego man. And that is also interesting because Lego was, let's say, invented in Denmark, which is very close to here. So also the Danes, when they speak about tomography, they like to present the Lego man. So it's a great example. So F here actually shows you a reconstructed slice of the Lego man. But of course, we cannot penetrate with visible light to see the inside of the Lego man. But in G, we have actually used X-rays. We used our lab scanner, which is here in the lower right corner at Lund University. So with that one, we can see the inside of sample. But these images shown in H and Y, they are actually so-called 3D renderings of the Lego man coming from my KBLT scanner. And here in I, we have color-coded the thickness variation in 3D. So something that is thinner gets a more purple color, and something that's thicker gets more yellow or whitish color. So all the steps, the workflow from scanning to reconstructing to image processing, image analysis are the same. We can use the same pipelines and workflow. So that is why this scanner is a good way to train new, let's say, students, scientists, let's say, industry representatives who would like to use tomography. Here is an updated version of the scanner. In the lower left corner, you can see that I have added a second LED light source, and this is because I want a even broader light, and this one I can use to scan even taller samples, while as with this one it's more beneficial when scanning smaller samples, and this one gives a more so-called cone beam effect, while this one we have more parallel light. But most features are, let's say, similar. Well, I can tell you that in this image, I actually updated to a Raspberry Pi 4, while in the previous I had Raspberry Pi 2. The Raspberry Pi 2 had to work a lot. So at some point I decided to change it, and I saved basically 30 seconds starting up the GUI. So it was a good investment, let's say. Here is an example of what it can look like when we scan a sample. I press the start button. Here you can see I had to press it twice, and you can see that here we're stepping. I don't know if you hear any sound from the video, but for every step we will rotate the sample over 360 degrees, and we will take 200 projection images. And you can see in the upper right corner here that we have a counter counting up to 200. So we're slightly more than halfway through, and after we have reached 200 projection images, there will be the time to move the sample outside the field of view, and we will, let's say, capture these so-called flat field images, which is, let's say, an image of the empty background, let's say. This LED light here is just telling us that a motor is moving, let's say. So now soon you will see the counter is adding up to 10. We take 10 flat fields, so we have a little bit of averaging to do. And now the scan part is done, actually. And it took 34 seconds. And now the sample is moving back to the original position. And after that, you will see very soon that the light switch will switch off. And it switches off in 3 simulated button presses. And I'm also being sent an email that the scan was successful. And then we can later on reconstruct the sample in 3D. But going to this 3D rendering, let's say, it doesn't go so fast. It can go very fast if you have everything optimized, but I will explain you how it actually works. So if you imagine that we acquire these so-called projection images around the sample, and then imagine that we store them in this way, let's say, and then we say that we want to reconstruct one test slice on this height where we have the blue line. Then we select just this pixel height. So it's 1 pixel tall. We select those pixel images from all these projection images, and we normalize them first, meaning that we divide it with a flat field and we apply a minus logarithm. And then we store them in a up and down, let's say, position. That will be called a so-called sinogram. And this sinogram we can use to actually back project, let's say, the intensities, let's say, into the center of the image, and then we can reconstruct the slice of this image. And if we reconstruct several slices, all the slices as this image here, the projection is tall, we can actually put them all together and create a so-called 3D rendering, as you can see here. And you can see that in the version 8, you can see that how much we improved in quality by having a let's say, rotation stage connected to Raspberry Pi instead of me manually trying to rotate the rotation stage in Lego, let's say. Very interesting is that also in 1980s for neutron tomography, they also had by chance 200 projection images, and they had a resolution of 1.3 millimeters. I would say that we are, let's say, slightly below 1 millimeter in resolution, but of course we cannot really see the inside of opaque samples. But we can see the inside in semi-transparent samples, let's say, or transparent samples. So if we present a little bit of physics, I'm sure many of you are aware of the so-called Beer-Lambert's law. We can rewrite that one in a way so that we get out the transmission. Here's a small example that I did with some bricks on a light table. I make it black and white first. We can measure the intensity, and we can set the intensity in the background to, let's say, 100. And if we divide the intensity from these ones with 100, we can make this plot based on the thickness of these blocks. And then we can actually extrapolate and see when does the absorption or transmission, let's say, go down to 0. And following certain ISO standards, one recommends that one should have a transmission somewhere between 10 to 20% in order to be able, in 2D, in order to be able to reconstruct something in 3D. Sorry. And the things that we actually reconstruct in our images are the so-called attenuation coefficient. So mathematically, we first normalize the images, we create the scenarios, we back project, and then in the 3D volume is actually the so-called attenuation coefficients that we will have represented in a grayscale from, let's say, on a 32-bit scale. Another small example, let's imagine that we scan, let's say, the chest of a human or a rodent. We can actually sum up here what, let's say, the sum of the attenuation coefficients, and they are E raised up minus, and then the sum of these attenuation coefficients. And if you would like to send secret messages to let's say, a friend, this is a small example I found on YouTube that I recorded a little bit. You can actually send them hidden, let's say, projection images containing numbers, and then you can ask them to reconstruct and figure out what 4-letter word you sent them. And I have exercises of this, let's say, 20 of them. If you take a look at X-rays and neutrons, this is the table of elements, but it contains more information. It actually contains the attenuation coefficients for either neutrons or X-rays. And these, for neutrons, they interact with the nuclei of the atom, while as the X-rays, they interact with the electrons. So we get different contrast behavior, let's say, depending on if you use X-rays or neutrons. And for X-rays, as represented here in blue, we have quite a linear dependency of the mass attenuation coefficient with respect to atomic number. But for neutrons, it's a little bit more spread out, but there is a sort of grouping going on here. But I would also like to take this example, which I borrow from the NIST in US. They scanned actually this toy car containing both plastic and metals. And these images here actually show you that with X-rays, they get quite a high contrast from the let's say, the cover of the car, because that one is made in metal, while as the wheels, which are made in plastic, they become quite transparent. But with the neutrons, they are more transparent to metal, but they absorb more of the, they're more prone to being absorbed by plastic. So by using X-ray and neutron tomography, you can get complementary information where, let's say, the sum of 1 + 1 might instead be 3 instead of 2. Yes, and this example I borrow from the NIST in US. Now, I also scanned some various toy cars. Here you can scan a small little toy truck, and here I also encoded it with respect to its thickness variation in 3D. I also then switched into some more transparent samples. So you can see that here I scanned this honey-based seed drink, and you can see directly on the detector screen that we are detecting the seeds because the liquid is quite transparent. And I also managed to reconstruct these seeds in 3D and also segment them, color them as represented here in H. And following the evolution of tomography, you always want more. Let's say if you have something in 2D or 3D, you want to have it in 4D, meaning could be time. If you have it in time, you also want to take into account so-called sample environments where you can modify your sample in some way. Maybe you compress it, you add temperature changes so that it melts, or you pull it apart, or you add water, let's say, and see how it sucks up the water. And this I also investigated. So I scanned this hourglass in 4D, so 3D plus time. And here on the right side, you can see a small animation of how this sand is actually falling down in the hourglass over time in 4D. And once I had established that, I took out a heat gun. So this would be my sample environment, and I melted some chocolate. And here in F, you can actually see how, let's say, the surface of the chocolate is changing over time in 4D, while B to E are the individual states over time. And once I had done that, one of the co-authors in the publication, he recommended me, you should take a look at a lava lamp, let's say. So I found a nice lava lamp that didn't have a cable, and that is nice because then it will not create any issues if you rotate continuously. You don't need a so-called slip ring. So I found one that had a so-called T-candle on the bottom. And this one weighed slightly below a kilo, I would say. So I needed to adjust the torque power of the rotation stage so that it could actually rotate this one. If I didn't have enough torque, there would be, it will rotate a little bit and then it will have a backlash and I wouldn't get any good reconstructions. This scan, of course, took a bit longer than the others. Here we're speaking about seconds, let's say, while here we're speaking roughly about half a minute, let's say. And I also, invented a small quote of my own that the design of sample environments is only limited by the user's own imagination or its academic or industrial relevance. So basically saying, just go a little bit crazy and test. You're here to learn, so explore. Now, the nice thing is that all this example that I presented to you, we can do exactly the same with X-rays, let's say. So in this example, in the upper left corner, we had scanned these steel rods coming from Swedish metal industry. And we have then, and they have actually been fabricated so they would contain some known defects, let's say. So we study a range of them. And you can see that these small darker pores appearing, they are let's say the defects or the so-called inclusions, and we can segment those as shown here in 3D, and then we can actually quantify their size, diameter, orientation, isotropy, and so on. Here in the lower left corner, you can see we made a study with another company where we looked into so-called wound dressings. So we actually have a sample environment where we're actually pumping in liquid to simulate that blood is going into this wound dressing. And this we did both over 2D, 3D, and 4D. So on the left side in the middle, you can see how it's pumping in 2D, and in 4D is actually a segmented 3D volume over time. Here in the upper right corner is actually a 2D example, but here we put some syringes from a pharmaceutical company where we varied the temperature and pressure, and we could actually detect at what given, let's say, pressure these syringes might start to leak, which is a problem if you transport syringes from A to B via various ways, for example, via airplane, let's say. And you want to know if there is a risk that they leak, because then you can construct them in another way. And then in the last example, this is a study we did at PSI, Synchrotron in Switzerland, where we actually scanned and baked bread in a microwave oven combined with convective heating. And the image on the left here shows you the dough at the start of the experiment, and on the right you can see a scan of the finalist bread at this given height. And this also has an industrial relevance apart from just being a very interesting example. So you can see that the scanner that I presented, my KBLT scanner, has many similarities, of course, with lab-based X-ray microtomography as in the upper right corner, with Synchrotron X-ray microtomography in the lower right corner, and with neutron tomography. You all need a source. You need a rotation stage, a sample, a detector screen, which we in the X-ray and neutron world we call a scintillator screen, which can convert let's say the X-rays or the neutrons to detectable electronic signal, let's say. And I also modified this plot from this article as cited here by Villarraga Gomez, and I added also the neutron tomography and also my KBLT scanner, where I approximate that it can be placed with respect to the diameter of the samples that will be scanned, and also on Y, the expected resolution, let's say. And to highlight where there are synchrotron light sources, there are around 50 synchrotron light sources all across the globe, and I will give a few examples here in Europe on the right side, and also in Northern America. So I can mention that I started my career at Elettra Synchrotron in Trieste in Italy, and then I moved as a master's and PhD student, and then I moved on to do a postdoc at DESY in Hamburg, and now I'm a researcher at Lund University, and also borrowed out to Max 4 Synchrotron, which is under Lund University. And I can also mention, since many of the attendees are from UK, that there is also a British synchrotron light source, which is called Diamond, and is located in Didcot. And next to the Diamond light source, there's also a neutron facility. And in the US, some selected ones, there is the Argonne National Laboratory, which is the home institute of the second co-author, Doga Gursoy, from the KBLT article. And there's also a nice synchrotron in California, in Berkeley. Here is a small example of some selected X-ray microtomography beamlines in Europe. I need to expand it, let's say, also to reach outside Europe. But you can see here that depending on your application and your let's say expected or wanted field of view, you can go into this list and see, does my sample fulfill these requirements? Do I need to change to another beamline? If I have any metals or softer materials, which energies should I select? And yeah, and what resolution can I expect? So that's always a choice you should do when you have a sample. But first off, I would start off with lab-based X-ray microtomography, and then see if there's a need to go to a synchrotron or a neutron facility. Some educational activities around the KBLT scanner. This is an image taken in Denmark. I actually transported the scanner to a PhD summer school. Below the table here, you barely see it. There is a small metal box, so I can pack the scanner and put it into this metal box, and then I can put it in the trunk of a car, and I crossed the bridge from Denmark to Sweden twice, one time every summer, and let's say for safety reasons, in case the customs would ask any questions, I always kept a version of the manuscript of the KBLT scanner close to me. Now it's also published, so it's not a manuscript anymore. Some more examples. There are companies that produce and sell smaller, let's say, X-ray equipment for educational purposes, as in this scanner from this company, 5W. And I can also show you this example. This is European X-Fel in Hamburg. They made an example of, this is a standard example that you always have, that you scan Kinder eggs, let's say, for the kids on if you have an open day. When my daughter saw this light, this is a fluorescent screen, so that produces a green light. She directly got a little bit sad because she wanted something pink. But once we opened the Kinder egg, there was actually a pink hair needle. So everything worked out. And then to put this in context, you can see the price tag of such a scanner. Now we're using X-rays. This is, of course, yeah, very nice. But if we speak about the KBLT scanner, we can, of course, press down the price, and one would be able to teach any, let's say, student researcher or representative from the industry tomography, even using normal lights, and we can then prepare them better for a future experiment with lab-based X-ray tomography or synchrotron microtomography or neutron tomography. So that's, let's say, one of the key reasons to having the KBLT scanner. Here's some examples from last year's summer school in Denmark. This group here, we had 2 project works. They investigated phase origami, so folded various samples, and this is inspired by another article on the, let's say, topic of doing tomography with visible light. And they also explored the phase contrast effects in rice paper or even folded plastic bags, where you get let's say, for samples that absorb very little, you might still get a very nice contrast from the edges, let's say, if you have the right scanning condition with sample to detector distance, let's say. Another group, they decided to image beer foam over time. So you can see here are reconstructed orthogonal views of the beer foam, and here they have managed to segment the beer foam that appears here. So when they started, they had a lot of beer foam, and then as time passed by, it became smaller and smaller. And then we step into, let's say, trying to develop user-friendly reconstruction frameworks or workflows for the users. I set up some pipelines in Jupyter notebooks based on TomoPy, which originates from the Argonne National Laboratory. This is Python code that is commonly used by many synchrotrons throughout the world. And I added some small features with, let's say, widgets, so one can pull these sliders to easier explore the data. And I also add a feature so we can, let's say, crop in live. So if the field of view is too broad, we can crop it down into save space, let's say, on the hard drives. And here we can also, very easily select the height of which slice we want to reconstruct. And we can also inspect the sinogram. And here you can see this is a small Lego feature. So this part is quite transparent. So here you can see even with KBLT, we see features inside here in the sinogram. And then we can optimize various reconstruction parameters. We can take a look at the sample throughout the different slice views. And we can, of course, also create a small 3D rendering, even inside the script. But there are also more dedicated software for doing 3D rendering. And in parallel, I have also worked on a small GUI for doing the reconstruction, also based on TomoPy and PyForms, and basically doing the same things that I showed you. And with a small button press, also starting a 3D renderer called Napari or any other 3D renderer, so we can go from projections to slice reconstructions to 3D renderings quite quickly and easily. The nice thing is that these reconstruction flows, either you have it in a Jupyter notebook for, let's say, the advanced users, or a GUI for the new users. A GUI can also be very, let's say, interesting and needed for advanced users or beamline scientists, because maybe they work late at night, and then it's nice to have an easy workflow. And yes, this I showed, and I can also let you know that the workflows that I developed for the KBLT scan, I also managed to bring to work, and we have managed to test them on real, let's say, data. And so one can say that there has been an interplay between my interest in the KBLT scanner and real work. So what I invent on the weekend for my KBLT scanner, I can bring to work on Mondays, let's say, and vice versa on Fridays. What is nice also, you can see that the real tomogram might go up to even 21 gigabytes, while as the KBLT tomogram might reach, let's say, 60 gigabytes or 100 gigabytes. So working with data sets from the KBLT scanner is also quite nice, because you can test it with your software on smaller data without having to test it on large chunks of data. So that this might help to speed up development. And I can also let you know that if you want to try out reconstruction in 3D, there is our data from the article has been uploaded to the TomoBank repository. So you can download this dataset by clicking here, and there's also a small reconstruction script for Python that you can download here. And this project with the KBLT scanner, as I presented it in various formats and conference. And so there were researchers just like Richard here who reached out to me. So one of them was actually the ESS neutron source, European spallation source, which is neighboring to MAX4. And they don't have neutrons yet, but they are building up their beamlines, and they are working on, let's say, hardware, implementation of hardware and software. And they wanted to be able to test out hardware and software related to tomography, even let's say 2 years from now, 2 years back. So we presented in the, let's say, our KBLT project, and they, with Samuel Staines here, who was a master's student at the time, and Stefanos Atansopoulos, who's also a PhD. Stefanos took a look more at, let's say, the acquisition from a software point of view and reconstruction, and Samuel Staines developed, here you can see a drawing of a nice, more contained version of the scanner with walls and so on. And this is, the video shows a very early version. But so it has spread, this project. Another researcher that reached out to me was Gianluca Iori. He's a beamline scientist at the soon finished tomography beamline called BEATS in Jordan, which is a synchrotron managed by UN. And they didn't have X-rays yet, but now they have, the X-rays have arrived. But he also wanted to test out hardware and software. So he contacted me, and we had a small Zoom meeting, and he then built a small setup to test out these things. And here he scanned some small spring in metal. And then he posted it and tagged me on Twitter that it worked. Thank you. And then I also have a collaboration with a researcher from France. So they have also, together with their master students and bachelor students, build a copy of the KBLT scanner, and they can train in tomography before they go to a neutron or synchrotron facility. And if you want to know even more about the KBLT project, I can tip you about that. I have created a so-called read the docs page called kblt.readthedocs.io, where I describe the code of acquiring tomograms or projection images, and this code is pointing at the code which you find on my GitHub page. And if you click on the lower tab here, you can also take a look at some various reconstruction or segmentation scripts of various samples. And if you can also tip about the fact that if you go under credits, you can read a little bit about some news coverage of the KBLT scanner, or you can also take a look at related educational projects which might involve normal light tomography. There are several persons who also investigated this in the past. One of the differences with our project with the KBLT scanner is that we're really trying to push down the time frame, so that instead of speaking about, let's say, acquiring a scan in 15 minutes, we're more down on 15 seconds, let's say. And we also involve the so-called sample environments, and we're trying to promote this as a project that can be useful both for students, but also for users or researchers working with tomography, so they can use this to test out their hardware and software so that it's actually working. So useful both for application scientists and let's say software developers. And please get in touch if you would like to build your own KBLT scanner in the future. I would be happy to communicate and guide you. And yeah, we'll be happy to do that, so that we can also fine-tune our building instructions a little bit. And with that, I would just like to highlight that this work with the KBLT scanner was published in a very new journal, Tomography Material Structures, by Elsevier, and it was actually the very first article in the newly established journal. So we were very happy, and also the editor was very happy. So please feel free to read it. It's open access. There's no subscription needed. And again, I would say that the KBLT, it doesn't matter what skills you have. If you're beginner or advanced tomography, beamline scientist, it's fun for everyone. Yeah, learning should be fun as I see it. And the KBLT can help you, as it helped me, to develop your electronics or motor control skills, IT math, reconstruction, image processing skills, knowledge about sample environments, and also physics or mechanical building skills. And with that, I would like to thank you all for listening, and please feel free to get in touch. And I also like to show this image, last thing I do, that I like to always say that imaging is just like an art. If you give us a little bit more time, we can create some magic. And with that, I thank you, and I will hand back the word to Richard. Thank you.
Thank you very much. That was really cool.
Thank you.
So let me let people unmute themselves in case they have any questions. So people can turn your videos on if you want. But yeah, does anyone have any questions? So I did have a question about the so the tuning when you first so you said you used 200 samples. So you
projection images.
Sorry.
200 projection images
okay,
around the sample. Yeah.
And why did you decide on that? Is that just a standard, or that just makes sense?
Yeah. So this rotation stage or stepper motor, by definition, its normal step is 200, let's say, steps per 360 degrees. But you can also implement so-called micro stepping. So you can even reach to 32,000 steps over 360 degrees. But I made some tests, and I realized that I didn't gain much from, for example, acquiring with 400 projection images instead of 200. Yeah. Most probably because we're speaking about visible light. But with X-rays and neutrons seeing the inside, it can make quite a difference having more projection images.
Did you try different lights and things like that? Like this, did your light source seem to be pretty much the same throughout, or did you have to change it to get something a bit better?
Yeah, so as I showed you that before, I started off with a smaller LED light source, which is super strong actually. But then I got the second light source, which actually has CPU cooling. And with that one, I can get much broader field of view, and I can scan taller objects. But I haven't really yet played with various, let's say, and ranges of visible light, let's say green color or blue color or so on. But people have recommended me this. So, but that's on the to-do list, let's say.
Right. And when you first built it, like when you first built your first Pi version, how long did it take you to get that up and running? Because it must have been very satisfying when you got a good image out of it.
Yeah, absolutely, it was. I mean, I think it was a matter of a week or so. I mean, I really liked that, I wanted to do something with a Raspberry Pi. I had a Raspberry Pi for, let's say, streaming videos via, home centers and so on. But like, I want to switch in more to motor controls and in a way benefit from that in work in some way. And then I got this idea and I tested it out, and then I bought the breakout board, cables, Raspberry Pi for Dummies, started reading, and with the help of that and having a project, you can a little bit with help with forums if you have problems, build up your own thing that never existed before. So that's how it started, let's say.
Yeah, it must have been very exciting when you first got your first images out. And
yeah, absolutely.
Very cool. I know that feeling when something finally works and you sort of say, yeah, that's good.
Yeah, exactly.
Something breaks almost immediately after that, but that's okay.
Yeah, I can also let you know I started Trello page and I invited colleagues and friends. So every time I did an update, I posted on Trello page and they would comment, and so it became like a virtual lab book, let's say. So that was, I mean, now when it's published, I didn't want to take it out to the world too early, let's say. I want to get the article out first, and now when it's open, I'm thinking about updating continuously on various upgrades in some way. So
yeah, I'm sure
I would be. Yeah. No, I'm really looking forward that more people start building scanners, and that this can be something that the world tomography community can work on, and for the better good, let's say.
Yeah, it does look a really great project.
Yeah.
So I'm taking a lot of question time. I don't know if anyone wants to ask a question. There's a few questions there, I think.
Yeah, in the chat.
I'll take a look.
You're worth having a read.
Yeah. Challenges initially, I would say that the most challenging thing was to get the rotation stage up and running. I mean, I would say that's the core of a tomography setup, let's say. I mean, getting the camera to acquire images, that's quite easy. The light source can be switched on all the time. So the rotation stage is really the core. And as I show in the article, one also needs to a little bit align so that you don't have a tilt of the rotation stage. If you do have that, you will not get nice reconstructions, let's say. So yes, infrared light, I'll put it on the to-do list. Let's see, have we tried different light sources? Yeah, I mentioned that before. Yeah, I think those were the questions, basically. Yeah.
Any other question people want to ask live or in the chat?
I asked if wiggler is a technical term because I saw it in that list of the various light sources.
It is a technical term. So there are bending magnets which will create a continuous, let's say, range of X-rays or infrared or ultraviolet light, and then you have the wiggler, which will basically force the electrons to go slalom, so you will get discrete, really high intense peaks. Or yeah, an undulator. Wiggler creates a little bit broader beam than an undulator, let's say. So there are these three ones to have in mind when, let's say, speaking about the synchrotron. And,
Yeah,
and you will put a certain magnet in connection to a certain beamline depending on which type of samples and which technique you have at the beamline. I mean, I'm into tomography, but there are also other beamlines that look at spectroscopy, looking what chemical composition do you have on the surface of a sample, or those that look at, let's say, the orientation of fibers in the, let's say, Ångström regime, let's say, but they don't get an image, but they will get a graph that can tell you what the orientation is of your sample. So there are, yeah, 3 to 4 different types of techniques and kind of subversions of them, or collaborations between this one. Yeah. So quite a lot to explore in X-ray and Neutron world, I can say.
Yeah. I really appreciate that you talked about 4D as well. That's where the scans in 4D, like that part as well.
Yeah, thank you. It's a lot of fun. Yeah.
Yeah, it does look like a lot of fun. I want to set one up, but I don't know if I've got time.
Please go ahead. Please go ahead. Yeah. But
Cool.
one can say, yeah, I mean, here we're speaking about tomography with visible light. I mean, there is also what you want to refer to as photogrammetry, which is, and to explain this, put everything in context. I mean, that's more when you create the 3D surface, let's say, as a photo of an object. But here we can actually see the inside of something in 3D, as I have the seeds in this drink, or I have air bubbles in a slime, or something in this way. So yeah, that's the difference between photogrammetry and tomography.
Very cool.
Okay.
Cool.
Thank you for listening, everyone. Thank you for inviting me, Richard.
I really enjoyed that. It's very, very good.
I will stay around and listen to Dane.